thank the organizers for organizing this very interesting meeting. So I'm not going to talk about particular research problems. I'd rather going to talk about give a brief introduction to certain field of research, and whoever is interested, I would be happy to discuss particular problems later. And maybe you'll see why. So this story starts with the dynamics in classical mechanical systems, and understanding this dynamics is important for various practical problems, including the motion of satellites, spaceships, and so on. And even in the most basic classical mechanical systems, dynamics can be really complicated. So here's an example. It's called three-body problem. You have three equal masses in the plane which act upon each other by gravitational force, and you will see that the dynamics here's the simulation of the dynamics for certain initial positions and velocities, and you will see that the dynamics may be really complicated. You can go like this forever and enjoy watching this. But let me go back to the story. So it's important to have some mathematical model of dynamics in classical mechanics, and the main approach to give such a model is called Hamiltonian mechanics. If you see about this stuff. So Newtonian mechanics, the setting starts with the so-called phase space of the system. So on the simplest setting is just R2n with the coordinates P1 up to Pn and Q1 up to Qn. It's the phase space of a system with n degrees of freedom. For instance, if you have 3-point masses in R3, then you have 9 degrees of freedom. So each mass has 3 degrees of freedom. So in total you have 9. And the coordinates Q describe the position of the system. So in this case, for 3 masses in R3, this would be 9 coordinates Q. And then you have also 9 coordinates P, which describe the momentum of the system. Momentum is the physical quantity, which is, in a sense, so this P1 up to Pn are sort of dual coordinates to the velocity. But if you are thinking about math, you can think without loss of generality about the speed as velocities, although physically it's not quite correct. But this is the meaning of this R2n. So each point in R2n describes the state of the system. Right? Classical mechanics state is completely described by the position of the momentum or velocities. And then there is an additional input. You have a Hamiltonian function. So the rest of the information about the system is described by one function called Hamiltonian function of Hamiltonian. It's a function on R2n cross R in general, and this R is responsible for time. So T is the time variable. So for each PQ in Rn, in each moment of time, H at that point describes the energy of the system at that state, at that given moment of time. Okay, and then you have the evolution of the system. Once the system is state starts to evolve, and this evolution is described by the classical Hamiltonian ordinary differential equations. So these are this system of first order or ordinary differential equations. And as we know from the first OD course, if you have such a system, then any initial condition describes a unique solution of the system. So to each PQ, for each PQ, for instance, you have a unique solution of T, which passes through that point PQ at the moment 0. And this solution is defined over a certain period of time, but let's for simplicity assume that all our solutions at all points are defined for all times. And then it makes sense to consider all the solutions at all points for all times together, as it's commonly done in ordinary differential equations. And this way you get what's called the flow. So DE defines a Hamiltonian flow of H. It's basically one parametric family of diffeomorphisms of R2. So diffeomorphism is the map, all of whose coordinate functions have all the partial derivatives full orders, and it has an inverse map with the same property. And if you fix particular PQ and look at the following mapping, which maps T to phi T of PQ, that's the trajectory, that's a solution, it should be solution of your ODE with the initial condition PQ at the moment equal to 0. And that's basically what's called trajectory of PQ under the flow. Describes how the system, which is originally in the state PQ, evolves with time. So this, at the moment T equal to 0, that's PQ, and then when T moves towards plus infinity or backwards towards minus infinity, you see the evolution of the system forward or backward in time, and that describes the evolution of your mechanical system. Okay, and in general, you can extend all the previous definitions to a much larger geometric framework without any coordinates, and in that framework, the phase space instead of R2N will be a general symplectic manifold. So it's a higher dimensional surface equipped with a certain differential two form with certain properties. And this gives rise to symplectic geometry. So you can study these manifolds, symplectic manifolds, mappings between them, their special submanifolds, and so on. So you just a general framework of a field in modern geometry. Yeah, that's a subject in its own. But if you're interested in dynamics, so this is what's called Hamiltonian dynamics. You want to understand the properties of the Hamiltonian flows, of the trajectories, and that's usually a difficult subject. Beyond the basic stuff that you learn in the first course on the subject, it's very difficult to say something on G, especially about large classes of Hamiltonian systems. So if you are thinking that maybe you can solve these problems numerically, then you have the usual trouble with numerical modeling of ordinary differential equations. If you want to model a long-time solution, then you are in trouble because your approximate solution and the actual solution may diverge with time. So there is an error which accumulates in your numerical methods, and your long-term solution may be way off the actual. The approximate solution may be way off the actual one. And also, if you are looking for a solution with a particular property, you need to understand first which solution you want to approximate. In any case, just simple numerical modeling won't help much. So you need to really understand what goes on. And the first basic probably the first basic property to learn in the first course on the subject is what's called an observation due to Liouville from the 19th century that Hamiltonian flows preserve volume. And that's you don't see it on the spot. It requires a certain minimal calculation, but it's relatively easy. So that was already known in the 19th century. And then there is a question: do Hamiltonian flows behave just like arbitrary volume preserving? Okay, maybe if you just study volume preserving flows, which is much more flexible object, you don't need any you don't need any Hamiltonian ODEs, right? Sort of maybe then we'll understand the dynamics of the Hamiltonian flows. And amazingly, the answer is no. And it took quite a lot of time to get to the point. And that's the really famous theorem of Gromov, called the Gromov-Snowsclear theorem from 1985, which says that no, sort of, for instance, here's the phenomenon which happens with volume preserving flows, but doesn't happen with Hamiltonian flows. So you have a round ball in R2N of radius R, and you want to move it into a cylinder. A cylinder in this case is a two-dimensional ball of a slightly larger radius than R plus epsilon for any basically positive epsilon times R2N minus 2. This is the cylinder. If you want to move your ball into a cylinder, you can't do it by Hamiltonian flow. You obviously can do it by a volume preserving flow. Just squeeze your ball by preserving the volume into a very thin, long sausage. And move the sausage by parallel translation inside the cylinder. But doing this with the Hamiltonian flow is impossible. And that's a really deep fact, which was apparently non-trivial. It was really surprising. And this gave rise, along with several other groundbreaking results from the same period, it gave rise to a new field of mathematics called the symplectic topology. So symplectic topology is basically about studying the properties of Hamiltonian flows that distinguish Hamiltonian flows from volume preserving ones. These are so-called symplectic rigidity phenomena. Something rigid that you see with the Hamiltonian flows that you don't see with volume preserving flows. Okay, so this is a new field, it's by now about 40 years old. And it studies, as I said, the phenomena that distinguish Hamiltonian flows from general volume preserving flows, and symplectic manifolds from arbitrary smooth manifolds. Okay. And what does it give you at the end? So let's understand well what it can give and what it cannot give. So it allows to prove existence of certain special trajectories of Hamiltonian flows. So periodic trajectories connecting between two different sets, and so on. It doesn't tell you how to find these trajectories. It also doesn't provide any information on typical trajectories. So that's a different subject. The methods of syntactic topology at the moment are not related to this question. Okay, they only can prove the existence, allow you to prove the existence of certain special trajectories. But even this information is really precious. The general situation in Newtonian dynamics is that any information is precious. Anything non-trivial that they can say is really precious. And this is so really precious. Okay, and what is special about the syntactic topology? It's I think among all the mathematical subjects, it's probably the one with the most connections to the other ones. At least one of the top ones in this regard. So it's related basically to everything, to most of the other fields of mathematics. So for instance, it's related to all other types of geometry, topology, and dynamics. It's related to various fields in algebra and analysis, real analysis, complex analysis, functional analysis. It's related to PDEs, it's related to mathematical physics. So it's really hard to find the field to which it's not related. Maybe logic, I don't know. Okay. Probability. Okay, but that's the real beauty of this subject. So it really allows you to see the unity of mathematics. The downside is that you need a rather extensive background compared with other fields in order to start your research. That's why I'm not discussing here particular research problems, because it's better to do it after you learn at least some basics and see what kind of things are studied in the subject. But I can say just one quick sentence that the specific problems that I'm interested in at this moment are related to connecting trajectories between different sets, to proving the existence of connecting trajectories between different sets. That's as much as I can tell you. Okay. And this is general description of the field. And just let me say one more thing. What's the main tool? Why people call syntactic topology? Where is the topology here? So the main tool here is studying of spaces of certain, they're called pseudo-homomorphic maps of two-dimensional surfaces, real surface of dimension 2, or complex surface of dimension 1, complex curves of dimension 1, complex dimension 1, studying the maps of such surfaces into syntactic manifolds, into these higher-dimensional surfaces equipped with certain differential tool form, and then using this spaces, topology of the spaces of such mappings, so we're studying basically not only the topology of the target space, the syntactic manifold where you map your pseudo-homomorphic curve, but the space of the mappings itself, right? And you use the topology of the spaces of mappings to extract various geometric and dynamical conclusions about your phase space or about the dynamics of your Hamiltonian flow. And here you already see the connection to complex analysis, pseudo-homomorphic curves. They're sort of homomorphic, not quite. Okay? And you see already the connection to functional analysis because you're going to study the spaces of mappings. You see the connection to topology because at the end of the day, you want to understand the topology of the space of mappings. You want to, then after you do this, you combine this logical information to certain algebraic structures, and then you see the connections to algebra. And this is just a quick mentioning of these connections. In fact, it's much more extensive and deep in various directions. Okay, so that's a quick introduction to the field, and I'll be happy to discuss with whoever is interested in specific problems. Okay.